Good morning, students. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC709. Topic laser. Laser stands for light amplification by stimulated emission of radiation. Basically, the optical principles are absorption, spontaneous emission, and stimulated emission. Regarding absorption, uh, if some photon of energy h mu instant on an atom, the covalent bonds will break in valency band and electron hole pairs get generated. The electron generated will enter from valency band to the conduction band, and this process is called absorption. Here uh, it is excited state E2, it is ground state E1. E2 state is unstable, means the electrons will stay a short amount of time and they return to the valency band. In spontaneous emission, the electrons from excited state will fall into the valency band by releasing the same photon of energy h mu, and the process is called spontaneous emission. And in stimulated emission, the electron is already in excited state. With the application of photon energy, it will fall from the excited state to the ground state by releasing double the photon energy. Now in this class we are going to discuss the principle of laser, Fabry-Perot laser, distributed feedback laser, DFB laser. Characteristics of laser. Laser has the following characteristics. The laser light is highly directive. It is monochromatic. Laser have the same frequency and wavelength as the photon applied. A laser is a high intensity beam. Lasers are coherent. Light emitted is of a single wavelength. Lasers have the same frequency and phase. Lasers can travel large distance. Principle of operation: absorption, spontaneous emission, and stimulated emission. These processes can be represented by a simple two-level energy band diagram where E1 is the ground state and E2 is the excited state. Just now we discussed, and according to Planck's law, the transition between these two states involves the absorption or emission of photon energy. Here, the energy gap between the states E1 and E2 is EG is equal to E2 minus E1, and here the excited state is unstable. Absorption: when a photon of energy h mu impinges on the system, the electron in state 1 can absorb the photon energy and then excited to state E2. E2 is unstable state. Spontaneous emission: E2 is unstable state The electron will shortly return to the ground state, thereby emitting a photon of energy that is equal to the energy gap between the two states. Now you can observe the spontaneous emission. In spontaneous emission, the electron is already in excited state. With the application of the electron is already in excited state. When it will jump from the excited state to the ground state by releasing the photon of energy that is given by h mu. It is associated with the energy gap between the two states. Stimulated emission. The electron can also be induced to make a downward transition from the excited level to the ground level by an external stimulation. Now here, if a photon of energy h mu impinges on the system while the system is already in the excited state, the electron is immediately stimulated to drop to the ground state and give off the photon of energy, double the photon energy of h mu. Now here, in this case, the electron is already in excited state. With the application of photon energy, uh, due to stimulated emission, double the photon energy gets generated. Population inversion. If the population of the excited state is greater than that of the ground state, this condition is known as population inversion. Since this is not a equilibrium condition, population inversion is achieved by various pumping techniques. In a semiconductor laser, the population inversion is accomplished by injecting electrons into the material at the device contacts to fill the lower energy states of the conduction band. This diagram you can observe uh, the pumping of electrons, how it forms the population inversion. Uh, Population inversion, you can refer to uh, the emission of multiple photons using stimulated emission of radiation. Here you can observe the emission of photon energy. Let us consider many number of electrons in the excited state. Means pumping is done and more number of electrons are present in the excited state. We know the photons emitted during stimulated emission have same frequency, energy and phase as the instant photon. And here you can observe uh, two photons applied on a device whose uh, uh, number of electrons are more in excited state. These two photons generates four photon elements with the application of population inversion. And here these four photons create double the photon energy, that is 4 into 2 equal to 8, and 8 photons are generated at the output of the device. Now here in this fashion the light amplification takes place. The next is Fabry-Perot resonator. It is the structure of Fabry-Perot laser and it is the lasing spot, or it is the position of active region, and these two are optical and carrier confinement layers. Here two reflecting mirrors are placed at one side and the other side at this position and at this position. The dielectric reflecting mirrors are placed, and the longitudinal dimension of the Fabry-Perot laser is 250 to 500 meters micrometers. In lateral direction, it is 5 to 15 micrometer, and the thickness or transverse direction, it is zero point 0.1 to zero point 0.2 micrometer. Fabry-Perot laser. It is a laser diode made of semiconductors, wise p-type and n-type materials. Uh, the construction of laser diode is similar to LED. The only difference is that active layer is made between the two semiconductors P and N. This active layer is often consists of quantum well and is made of an intrinsic semiconductor. Once again, let us refer to the structure. Here, these are the position of mirrors. It is active layer where, due to stimulated emission, photon energy gets generated. The generated photon energy travel back and forth between the two mirrors, the reflecting surfaces, and forms standing wave pattern. And the photon energy associated with standing wave pattern will come out as laser light. Now here, if you observe this diagram, it is the instant energy, and it is the reflected energy. Here there is no relation between the instant energy and reflected energy. They are not meeting at a point, so it doesn't form a standing wave pattern. And if we observe this diagram, it is the instant energy and where it ends at this point, at which the reflected signal starts, uh, and this pattern is called standing wave pattern. And the photon energy associated with the standing wave pattern, which moves back and forth in active layer, will come out as laser light. Fabry-Perot resonator laser supports infinite number of wavelengths, some modes under gain and some under loss. Uh, these modes under gain and the remaining under loss. Distributed feedback laser or DFB laser. In DFB laser, the optical resonator structure is due to the incorporation of Bragg grating or periodic variation of refractive index into multiple multi-layer structure along the length of the diode. Uh, the structure of DFB laser is similar to the Fabry-Perot laser. The difference is it is Bragg grating. In Fabry-Perot laser, the reflecting surface will act as resonators, but in case of DFB laser, Bragg grating layer is incorporated. It is associated with the variation of refractive index into multi-layer structure. It is along the complete length of the device. That is the difference, constructional difference between Fabry Perot laser and DFB laser. These two are confinement layers, and it is active layer where the laser light will come out. And here, due to stimulated emission, the laser light, the photon energy gets generated in active layer, and the generated energy are reflected by the reflecting surface called Bragg reflector. Uh, some basics about DFB laser. It is a distributed feedback laser used for single mode fiber. It is used to generate the signal with single frequency. DFB laser is less susceptible to temperature variations. It has diffraction grating above the active region, which provides reflections. The diffraction grating function as Bragg reflector. The periodic variation or variation of refractive index is obtained using diffraction grating. The reflector reflects the signal which are near Bragg wavelength and other gets suppressed. Just now we discussed the photon energy which generates reflected by the Bragg reflector, and here the Bragg reflector reflects the signal which are near Bragg wavelength. The, the signal which are near the Bragg wavelength gets reflected, and the other signals gets suppressed by the reflector. And the energy of photon which gets reflected will come out as laser light. That is the basic operation of DFB laser. Once again, I repeat, the reflector reflects signals which are near Bragg wavelength, the other gets suppressed. And the photons which are near Bragg wavelength are responsible for the lasing action. The fabrication of DFB laser is similar to Fabry-Perot type, except that the lasing action is obtained from Bragg reflector or grating, that is periodic variation of refractive index. Output radiated power of DFB laser, output power versus injection current, wavelength, intensity. You can refer to the graphs. The DFB laser is mostly used for single mode fiber as it generates single frequency. The power output of LED versus laser. Refer to the diagram. Thank you. We'll meet with the next lecture.